Hello my dear students, in these slides I am going to discuss about the optical instruments which we are using in our today life for the purpose of seeing the smaller thing as a bigger one, or I want to see the object which is far away, I can't see that one clearly, that's why I am using one more instrument. So for these purposes whatever we are using, how they are working we are going to see in this particular video. Simple microscope, first one. So a simple microscope is used for observing magnified images of the tiny objects. Very small minute objects can be seen by using this microscope. So for example, for the reading purpose of a screw gauge or a vernier calipers, you might use already the convex lens. See, that is nothing but a simple microscope. It is a converging lens of a small focal length. Converging lens means convex lens. When the object is placed closer to the lens at a distance lesser than the focal length of the lens, the virtual, erect and magnified image is formed. The image formation by the convex lens you studied, in that if the object length is less than focal length, the virtual erect image is formed behind the object with magnified value, right? A ray diagram for the simple microscope when the image is formed at a least distance of distinct vision. What is this least distance of distinct vision? For the human being, that is the minimum distance from the eye for which he can see the object clearly and distinctly. Okay. So less than that one, it will be blur. More than that one, it is clear, but it is appearing as a smaller. So that is a particular distance from the eye, so at which he can see the things clearly, and below that one it will become blurred, magnified, but we don't want it. When it is moving away, it will become a clear, but it is not a magnified. So it is just like by keeping the paper while reading it, keeping at a distance, not closer to the eye, right? So that is the way we are using here. So it is closer, and that distance of distinct vision is known as, it is the minimum distance from the eye for which the person can see the things distinctly and magnified. So this is the convex lens, this is the principal axis, AB is the object, and this is the lens, convex lens. See, this is a real object. For example, it may be a book or it may be any instrument which is having a minute scale sizes. This is object distance, and these are the ray coming from the head. They are diverging like this. They are moving. They are moving, but they are diverging. When you're going to see from this side here, the eye focused on the near point, right? So when eye is focused on the near point, the rays are appearing like it is formed at a distance of the near point D, where near point D for the common human being is 25 centimeter. The linear magnification M for the image formed at the near point D by the simple microscope is. What is the meaning of linear magnification? How much bigger I can see the object by using this microscope. This is a single lens. Okay, that is called as a magnification, simply called as magnification, but its actual word is linear magnification. Yeah. So how we need to define linear magnification is ratio of image distance by object distance. Yes, we have the thin lens formula. By that one we can substitute the value of 1 by u as 1 by v minus 1 by f, because 1 by f is equal to 1 by v minus 1 by u, it is the formula. We want 1 by u, so 1 by u is taken to the left side, means 1 by f is taken to the right side. So negative value will become positive and positive value will become negative. So here 1 by v minus 1 by f we are getting. So 1 by u can be written as 1 by v minus 1 by f. Now magnification we can find here by taking this 1 minus v by f by multiplying v both sides. Applying sign conventions, v value is nothing but it is minus d distance, because it is the near point distance or least distance of distinct vision, and f is here capital F. So minus of d is taken to the value of v. 1 minus of minus d divided by f will become 1 plus d by f, where f is the focal length, d is near point or least distance of distinct vision. Ray diagram for the simple microscope when the image is formed at infinity. See, first case, whatever you studied, that is for the strained eye case. See, whenever you are reading the book, so from the closer point, you may feel that when there is a tiredness in your eye. So I want to get a relax. What we will going to do? We are keeping a book aside and we are seeing the larger distance related object. So that the rays which are entering your eye will become parallel. For the parallel case, eyes are relaxed case. When it is taken at the near point, eyes are under stress because ciliary muscles are working based on the value which can be taken on the retina case. That's why in this case it is taken as a relaxed eye case when the rays or image is formed at infinity distance. See, this is a lens, this is the principal axis, this is the object kept and which is having a height h. This is nearly at focus only we kept. The rays are coming like this from the head. They are forming the parallel refracted rays. And when you're going to see from this side, so rays are meeting at infinity. That means rays are coming parallelly to your eye, means eye is under relaxed condition. So the angles are same here. Now we can define the angular magnification as it is the ratio of the angle subtended at eye by the image to the angle subtended by the object at eye. So angle subtended at eye by the image tan theta I is equal to, so we can take, it is very closer because it is a paraxial, means it is very closer to the principal axis and it makes a smaller angle. For the smaller angle, tan theta is taken as theta. That is equal to h divided by focal length f. If h is the height of the object and d is the least distance of distinct vision, then in such cases tan theta naught is equal to theta naught initial angle h divided by d I can take. Angular magnification where m can be written as theta I divided by theta naught. Okay, angle subtended by the image I and angle subtended by object at I, that is equal to h divided by f divided by h divided by d. So magnification we can find by using this, hh get cancelled, d by f. So you can compare this one for the near point and the infinite distance. For the near point 1 plus d by f, and for the infinite distance it is d by f. That means magnification is maximum at near point. D indicates least distance of distinct. Now compound microscope. A simple microscope can be limited magnification. It is having a limited magnification. We can't see much more magnified. For a such larger magnification, compound microscopes are used. You want to see the microorganism, you are using the microscope, right? Compound microscope you are using. By the simple magnifying glass, you can see the microorganisms. So for that purpose, we are using a compound microscope. Compound microscope consists of two converging lenses. The lenses nearest to the object is called as objective O. It forms a real inverted magnified image. This serves as the object for the second lens called as eyepiece. It produces a final image which is enlarged and virtual. See, this is the objective and this one is eyepiece. This is the principal axis which passing the both optic centers of both lenses. Object is kept towards the objective lens and height of the object is h. This is the real object. And the rays coming from the head are forming the head image and object distance is u and image distance value will become v for this case, and it passes from focus and they are meeting at a point and the ray which is directed from optic center undeflectedly, that is moving. Here the image formed by the first lens will takes place, that is this one, and this is taken as h dash, and this image act as a virtual object for the second one. and rays which are going, when you're going to see from this side, it appearing like magnified image is formed, A double dash B double dash. So at a near point means we are taking it closer to the eye only. At a 25 centimeter we are forming it to see magnified. From the similar triangles we have, these two are similar triangles. Minus h dash divided by h is equal to L divided by f naught. This gives rise to h dash by h is equal to minus L divided by f naught. Magnification produced by the objective, because there are two lenses, we want to see what is the magnification produced by the objective and the eyepiece separately. So magnification produced by objective is minus L divided by f naught. Magnification produced by the eyepiece, that is ME, is equal to 1 plus D divided by FE, because already in the previous case magnification for the single lens we studied, the same formula we are using here, right, for the eyepiece. Eyepiece is nothing but a simple microscope and image is formed at D. Total magnification. Total magnification M is equal to M naught into ME. It is a product, not a sum. Note here, it is a product, not a sum. So product of magnification produced by the objective and product and magnification produced by the eyepiece. So total magnification is minus L divided by FO multiplied by 1 plus D divided by Fe. So remember student, they are not going to ask the question for the obtain an expression for magnification, but they are asking only write the expression for magnification in the examination. You need to memorize this last point of this particular derivation. You need to remember. So net magnification is the product and the value of magnification in the cases of compound microscope when it is the image is formed at a near point or least distance of distinct vision. The negative sign indicates that final image is inverted. Here L is the length of the microscope tube. D is the least distance of distinct vision. F naught is the focal length of objective. Fe is the focal length of eyepiece. Now telescope. A telescope is an optical instrument which is used to see the distant object clearly and magnified. This is the telescope. It has an objective and an eyepiece. Here the objective has a larger focal length and a much larger aperture than the eyepiece. Why we are keeping much larger aperture? To collect a large number of light rays so that the image formed is clear and distinct. Ray diagram for the image formation in a telescope case. These are two lenses. One is objective with a bigger aperture, eyepiece with a smaller aperture, and this is the principal axis. Rays coming from the top, if they are parallel, they are forming the image at the focus. They are forming the image on the focal plane. They are forming the image on the focal plane. So this is the image A dash B dash. Somewhere AB is there, that is the object. For that one image is forming here as inverted with a height h, and angle made by the incident ray with the principal axis is alpha, that is with I only. So FO is the focal length, on the focal plane only it is forming, means the image distance will become FO, and the rays which further moving for this particular image formed by the first lens act as a object for the second lens, and the rays are going and we are seeing the image of this. The magnification power M is the ratio of the angle beta subtended at an eye by the final image to the angle alpha which the object subtends at the eye. So hence magnification M is very closer to beta divided by alpha. So beta is angle subtended at the eye by the final image and alpha is the angle subtended by object at the eye. So tan beta, I want to find out beta, so I am taking this tan beta, and for the smaller angles tan beta will become beta. So that gives rise to minus h dash, or h dash we can take, divided by minus fe, that gives rise to h dash by fe. Similarly, tan alpha we will take, that is very closer to beta because it is also the paraxial ray. Paraxial ray means they are closer to the principal axis, they forms the angle very less. For a smaller angle, tan angle is angle only, so therefore tan alpha is equal to alpha. That gives rise to minus h dash divided by fo. Now, by taking the magnification formula beta divided by alpha, we are substituting the beta h dash divided by fe divided by alpha, where denominator term will go to the numerator and numerator term will come to the denominator, that is fo divided by minus h dash. So h dash get cancelled and minus comes, fo divided by fe remains. So this gives rise to minus fo divided by fe, where fo is the focal length of the objective, fe is the focal length of the eyepiece. The length of the telescope tube totally can be taken as FO plus FE. A reflection telescope, that is a cassegrain telescope. The modern telescope use a concave mirror as objective instead of the lenses. Why we are using this one? Because using a lens which is having a more aperture, it is a more critical condition to handle it because of a more mass, and it must be made up of a glass, means it is heavier one, so it is difficult to handle. Therefore we are using a reflecting medium which is of a lightweight. So by using the mirror we can create it. So modern telescope used a concave mirror as an objective instead of a lens. Telescope with a mirror objectives are called as a reflecting telescope. Now this is a schematic diagram for the cassegrain telescope. So this is the objective mirror which reflect the light. See, this is the mirror we are using. Basically it is a convex mirror, a secondary mirror we can say. This is the eyepiece through which we are seeing. The rays are entering from the aperture part and they are incidenting on the objective mirror. They will reflect back, and after reflect back they are incidenting on the secondary mirror which is a convex mirror, and divergence will take place because laws of reflection is also obeys. They are meeting on the eyepiece. So when we are going to see that one from the eyepiece will magnify it and it will show the image of that. This is a cassegrain telescope. Advantages of a reflecting telescope we are going to see. There is no chromatic aberration in the mirror. Chromatic aberration means splitting of colors and make it appear as different colors. So in the telescope, reflecting telescope, there is no chromatic aberration because we are not using the lens here as the aperture or a objective lens. Therefore, there is no chance of getting the color splitting. Therefore, it is called as aberration. Chromatic aberration is not produced. If the parabolic reflecting surface is chosen, the spherical aberration is also removed. Because of a spherical shape, there is aberration is taking place, splitting of color is taking place, that can also be removed if we are using parabolic reflection surface. Mechanical support is much less of a problem since a mirror weight much less than the lens of the equivalent optical quality and can be supported over its entire back surface. See, if the objective is used as a lens, the much more bigger lens we need to use which is having a much heavier, it is very difficult to handle that one. Therefore, by using the reflecting telescope, the reflecting portion which is light weighted, it can be easily handleable.